I think we can start with the introduction, and I think I'm sure that more people will log on when we are a little bit further with the session. So good morning, good day, good afternoon, everybody in this IMA webinar. We have been out for a while with webinars because we have had our annual conference at end of August in Barcelona, and we have decided to keep the webinar series because it was very successful in the past, and also we had about 100 people registered for the 120 people registered for the session today. So my name is Martin Tauber. I'm the European representative of the International Magnesium Association, and together with Lee Helgen, Executive Vice President of the IMA, Rick McQuarrie, President of the IMA, and Ken White, the European Chairman of the IMA, we welcome you to this webinar, which is titled New Developments in Magnesium Molding and Casting. We'll have three presentations from three member companies, from Meridian Lightweight Technologies, from GF Casting Solutions, and from 595 Solutions. So all IMA members, so I'm very proud to be able to present within the membership this event today. Just some householding announcements. This webinar will be recorded and it will be available for the participants on the IMA website, and also available on the IMA YouTube channel. And the presentations will be one of course in order, and then during the presentations and shortly after the presentation you can ask one or two questions if it's urgent, using the chat function, and at the end of the event we're going to allow also such more time for a Q&A, depending on the left time as we have. So from now on, please keep your microphones muted, only switch them on when you are asking questions. Cannot go further with my slide. Okay. Yeah, before we start, for whom you're not knowing the IMA already, the International Magnesium Association is the global voice of the magnesium industry. We are there since a long time, since 1943, representing the complete value chain of the magnesium industry. So starting with primary producers, secondary producers, recycling companies, tier 1, tier 2, tier 3 companies, OEMs, institutes and universities, but also, for instance, consultants to the industry or equipment suppliers. We normally do our flagship event. It's one time a year annual conference. So we just said that we had the last one in Barcelona, and the next one will be next year in May in Calgary. So mark your calendars already for this event. What you can expect now in the next, let's say, 1 hour 20 minutes or so. You had already the IMA introduction. Then we show you a small teaser for the industry, especially on casting. And then we have our three presentations. And then we have a Q&A. I would like to open up the discussion here a bit, and for the presentations to come. So we made a small questionnaire for our member base, and this was done for the Eurogus this year in June. And this is a little bit on die casting, but I think it reflects a little bit the whole industry. So we see within the IMA the OEMs, new request or there's a new need for weight reduction. So we saw that the emphasis on the battery and something is still on, but there is again the need to make the cars lighter, and also to look in that respect also for new application. We have from let's say traditional die casting parts, we see a trend to for instance Thixo-moulding, where we have a presentation today as well. That means electrification of cars will require a new type of parts, and these are also served and made via other technologies as well. The same with 3D printing. I say it's coming for magnesium, but it's not that far advanced as for instance with titanium or aluminium. We'll have a presentation on larger machinery as the gigapress or mega press. So we'll hear a little bit later on that. Magnesium industry has always had and has a bright development on new alloys, because in principle we are serving the industry since many years with a few commercial alloys. So that will open up in the direction of new application in terms of high temperature or corrosion, and especially that for the changing of the car infrastructure and so on. So we'll have opportunities for classical parts to go over from a combustion engine car to a new electrified car, but we'll have also some opportunities for other parts. Threats what our membership saw for the industry is of course the CO2 footprint discussion on primary production in magnesium, the recent price development between magnesium and aluminium. We saw that with the supply crisis end of last year and the supply interruption. And of course, we had a little bit a short-term loss of lightweight focus, which is now back. And then we have the common sentiment about magnesium on corrosion and fire risk, and etc. And we'll have the need for greener production, which we as an IMA also addressing within our membership for the years to come. With that, I think I would like to give the word to the first presenter. And the first topic is trend towards large die castings magnesium viewpoint, presented by John Weiler, Chief Engineer at Meridian Lightweight Technologies. John is Chief Engineer at Meridian Lightweight Technologies, and he has been at the company since 2012. He has a PhD in materials engineering, and he has nearly 20 years of experience in lightweight automotive materials research and development, specializing in magnesium cast alloys, and currently serves on the IMA board of directors and also is for many years the IMA award chairman. So over to you, John.
Thank you for the kind introduction, Martin, and thank you everyone for joining this webinar today. We have some excellent presentations that we're looking to go through today. So as Martin mentioned, I'm going to be going over the trend towards large die castings from a magnesium viewpoint. So just going to make some key points today in the presentation. I'm just going to go over what we all know about aluminum large die casting implementation, some market adoption of these types of castings, some of the enabling technologies that allow these castings in aluminum to get to these giga or mega sizes, and then what that means for magnesium. There's some key takeaways I want to impress upon everyone, and I'll get to those at the end of the presentation or as we're going along. So the first one I want to make, first impression I want to make is when we're talking about magnesium structural castings, and this has been true for a number of years, the key that we're always presenting to customers and industry is part integration and consolidation. So we're able to get some mass reduction, reduction in number of parts, and assembly steps for the OEM. In addition to good accuracy and stability, you get some good dimensional stability through casting in one large shape versus weldments or assembly of multiple components. And you get the complex shapes in a single process step. And as we all know, Tesla's implemented these large or giga castings on the Model Y. And this slide that Tesla's put out, I think a couple of years ago, they're showing their part reduction. So they're integrating a number of parts, consolidating parts. Obviously, it's a number of part reduction. It's an assembly reduction in their plant, and they do get some mass reduction in doing this. And again, accuracy and stability, and they're casting this complex shapes into one step. So in essence, what Tesla's accomplished here is what we're always pushing with structural magnesium castings. So we're looking at the same type of benefits. Some of the other benefits that Tesla and some other OEMs are impressing upon the market with going to these types of castings is, as I mentioned, the weight reduction, which translates to range improvements. There's been a reported 10 to 15% weight reduction with these types of castings. Assembly reduction, so in the OEM's assembly shop, they're seeing about 30% reduction in floor space, and Tesla's claim there's 300 less robots that they need to implement. Of course, NVH and manufacturing complexity is improved, and capital costs, energy reductions in the assembly shop. The supply chain is going to be much more simplified versus a multitude of components and different materials. And also the improved material utilization, including secondary metal. So there's been reported that the plan is to use by I think it's Volvo, up to 100% of cast material and including 50% recycled material. So we're seeing a lot less waste, and we're seeing correspondingly reductions in CO2 emissions and material usage in going to these types of castings. So global adoption. So since Tesla started this a number of years ago, what we're seeing is Volvo has invested in what they call mega castings in Sweden. So they're getting into this type of these types of castings and ordering large tonnage machines. Volkswagen has aimed to get into this type of casting. Mercedes-Benz also is reported to start using these types of castings. And NIO as well is working with a supplier to introduce these types of large castings. So we're seeing European OEMs, we're seeing some Chinese adaptation here, but we haven't seen anything in North America up to this point. What we're seeing also is it's strong from OEMs with internal casting capabilities or strong partnerships in the case of NIO. However, we're not seeing this type of adoption everywhere. BMW is, as of last year, almost a year ago, is planning to not implement these due to their evaluation of expensive repairs, casting costs, and they have other efficient methods to manufacture the chassis in their electric vehicles. So some of the technology enablers that have allowed this type of large casting is die-cast machine design and controls evolution, improvements in the die-cast tooling, casting design for increased energy absorption, and new aluminum alloy compositions targeted for these types of applications. So I'm going to go through each one of these and kind of give some information on how these have evolved or improved over the current standard from the last several years. So die-cast machine tonnage, this is a slide from Bueller in 2010, where we're seeing 4,400 ton machines available on the market, all the way up to 2017, where Mercury Marine is advertising a 4,500 ton machine as the largest in North America at the time. So not much size growth in those number of years. And then we get to 2020, up to a 6,000 ton machine by IDRA. And then later on that year, we're looking at 9,000 ton machines. And then even further, we're looking at 12,000 ton machines that have become expected on the market. So we're seeing quite a large growth in the size of the machines, enabling these large and even larger types of castings. So controls evolution, a number of the die-cast machine OEMs have improved in a number of different avenues, their machine design and their controls, including in the injection systems and in the hydraulic systems, looking at closed loop regenerative injections, reducing cavitation of the oil from the traditional designs, and then increased pump capacity through separating the closing and injection systems, and then looking at high flow hydraulic manifold blocks. So we're seeing beyond larger machines, we're seeing evolutions in the controls, enabling a better control and better precision castings in the machines. And we get into large casting tooling improvements. So we're seeing improved thermal management, so multi-zone die heating, micro spray for die lubricant, shot sleeve technology. So we're looking at heating and wear replaceable inserts to account for the thermal expansion. We're looking at plunger tip design and different material selection. And of course, venting and air management. We're looking at different chill vent designs. We're looking at modular vacuum systems with multi-channels to improve the evacuation of the die. And as well, we're looking at casting design for energy management. So as the electric vehicle design has moved towards a new architecture with structural battery packs, we can enable these large castings, and the casting design process, so putting in the typical ribbing, variations in thicknesses, looking at transferring the load efficiently. We're able to use alloys with limited ductility versus the traditional wrought alloys that are used in these types of applications. And even further, there's been some designs in these types of castings to induce energy absorbing features. So the use of C-sections and I-shaped central ribs with waveform profiles, cutouts, scalloped ribs, enclosed sections, tapering in axial direction, and this is a excerpt from Tesla's patent application, where they have this type of design to be able to absorb energy in a crash situation, which they show in this image here, where they're showing the casting section absorb all the energy and rather than buckling right away. And the last thing, the last enabling technology is new aluminum alloy compositions for these types of components. So there's been a lot of development in aluminum alloy compositions over the last number of years. What Tesla's looking at is an alloy that they're utilizing an optimization between strength, ductility, and castability without any subsequent heat treatment. They're looking at a yield strength of about 130 megapascals The measure of ductility, they're using a bending test. So they're looking at a 20-degree bend angle of a sample, and they're looking at high flow length. So this is the alloy that they've looked at for these types of applications. So what do all these things mean for magnesium? And I'm going to start with the more simple things. So most of these improvements are beneficial. So getting better controls on the die-cast machines, new die-cast tool improvements, and optimizing the die-cast design. These are just going to help magnesium. We're going to improve the consistency in the process, the ability to control with the tooling, different thermal zones, with the controls on the machines, and of course optimizing the cast design. We can look at different ways to optimize the weight and performance of the casting. The two I've saved are the size of the machines and the alloy. So this slide goes over the size of the machine. So generally, magnesium castings require smaller sized machines than similar sized aluminum castings. And an example I have here at the bottom is a part that was in starting in 2004 in the Dodge Viper, the front of dash casting. So it was designed to contribute to chassis torsional stiffness and weight reduction. At the time, the Viper team reports it as a magnesium cowl super casting. It measures about 1.6 meters by 0.6 by 0.5 meters, and it's about 10.6 kilograms in magnesium. Now, if you had to cast this type of casting in a aluminum, it would have required a gigacasting machine at the time. It would have been beyond any tonnage that was available on the market at the time. So in essence, as the Viper team reports, in magnesium, we have had these types of super castings for several years in magnesium. And then the last one was the aluminum alloy. So again, the aluminum alloy was developed for strength, ductility, castability with no heat treatment. So these target properties we're looking at, so yield strength of about 130 with good castability and no heat treatment. It's sounding a lot like a typical high pressure die cast magnesium alloy. And when we look at the bend angle, we see that we are comparable between commercially available magnesium alloys and the alloys that Tesla developed in their patent. And you can see that in the graph here. In the orange is the family of alloys that Tesla developed, and obviously there's a range of yield strengths and bend angles. And there's 4 points here in the magnesium alloys, and these are alloys that are available commercially every day. And as you can see, again, there's a commonality between these two alloys, between the magnesium and the aluminum, is you're going to have a trade-off between the strength and ductility. Well, what I wanted to highlight is the alloys that are being developed for these types of castings and the properties that they're demonstrating are available already in the market for magnesium alloys. And as you're picking your application, you want to be able to utilize the alloy that you see fit and that fits your properties that you're targeting. So again, what I wanted to impress upon as the key takeaways is as we've seen, the large castings are being implemented in electric vehicle applications. Several different OEMs are looking at this and implementing it in their vehicles in the future, enabling technology developments in equipment design and alloys. And these are all favorable for magnesium die castings. And again, we have had similarly sized or very large type magnesium castings in several applications over the last number of years, which when we get to these larger size machines, we're just looking at potential for even larger magnesium die castings. So I wanted to thank everyone for your attention today, and I think we have some minutes for some questions. Martin?
Thank you, John. That's a very interesting presentation, and also a good takeaway that the magnesium industry has already done giga castings without naming it giga castings. I think that was the big success, because magnesium castings combined a lot of single parts into one for the instrument panel or for the front ends. So this is a typical magnesium application, which you are also finding in the electrified platform of today. So those parts went over to the new platforms. Do we have any questions? I don't see any questions at the moment in the Q&A. So we'll leave the questions to the Q&A session. And I would like to introduce the second speaker, who is Michael Just from Georg Fischer from GF Casting Solution. And he will talk about from megatrends to innovative castings system solution. Michael holds a degree in foundry technology and has been working for GF Casting Solutions since 2006, where he represents the area of materials and process development, especially in the field of light metals. Currently, he's working on topics of fiber composites, smart castings, and material simulations using aluminum to develop future requirements at an early stage using chain simulation. And I hope he's working also on magnesium developments. And he's also serving on the IMA board of directors. So over to you, Mike.
Thank you for the kind introduction. Hello, everybody. You see and hear me? Martin?
Yes, yeah, everything is clear.
Okay, fine.
And your slides are on. Thank you.
Oh, also fine. Okay, I will start directly with some quote, amusing quote from Mark Twain. The human brain is a great thing. It works right up until the time you stand up to give a speech. And this quote always accompanies me, and at the same time sensitizes me to the opportunity to such a lecture. And therefore, this presentation should be understood as an opportunity to develop new ideas and products every day. Who of you had a first idea today? Maybe in the train or in the car traveling to office. I myself often have good ideas as such lectures, and I like this one, and hopefully you can develop at least one own idea after this lecture is done. First of all, I would like to present you the opportunities that we foundrymen have, and not, as it is so often and the case in today's world, just only the challenges. In order to do this, we must, of course, translate the megatrends of our times and use in order then the derivation to our companies. Subsequently, innovation must be recognized. And how can this look like? I will show that with some examples. And of course, we will also take a small look to the sustainability. Okay, this map represents the trends of our times. It shows the intensive interactions between the different disciplines. If you only look at the route of mobility from here to here, you see that the security, connectivity, urbanization, health, and so on influence these megatrends, or the mobility influence the other trends. It is a powerful tool, but difficult to use, and needs to be simplified for the derivation of product strategies. In the following simplified example, I would like to present a possible derivation for the development of make it more touchable. Okay, as you can see, I have picked out 3 megatrends and divided them into subtrends, technologies, and development fields. I would like to explain it briefly using mobility as an example. The subtrends, autonomous driving, e-mobility, and bike boom are certainly real subtrends for our industry. The technology fields of alternative vehicle systems, electrical powered vehicles, smart castings, and mega casting, which can be identified here, among other things, are really known. The development fields that results from such a battery system, power electronics, e-motors, charging stations, fuel cells, closed sections, and high-pressure die casting, are specific ways to derive product strategies, but you don't have still a product strategy. And therefore, I will show it. I show some examples for that to make it clear. As you can see, I have picked these out 3 megatrends and divided into subtrends here. Yeah. Okay. We're going to the batteries we already have today. What you can see here is if you compare the existing lithium-ion battery to the possible coming solid state, it becomes obvious that this is a good chance for the foundry world. As you know, the batteries gets bigger and bigger, and these mega castings are difficult to cast. Therefore, a lot of battery trays are built up from sheet metal. If now the energy density, as here proposed, there is no need for such big battery trays, and we can cast it with existing equipment. This is, of course, as well a sustainability effect. Furthermore, the secureness and the quick charging times will be massive door opener for this technology. Mega castings. As John already presented, I have also some notes for that. The big topic, mega castings, will guarantee a chance for development in the foundry business. These big castings have an issue with distortion, and therefore you will prevent the heat treatment. Cast alloys compared to the broad alloys have some challenges to perform in the same way like sheet metal. Therefore, you need some nice ideas to design. You can develop that by hybrid casting. You can create crash alloys. As I already mentioned, smart products designs is a key or door opener. And as well, the joining technologies, all chances for die caster. NVH, you can provide with compound casting, closed sections in the hybrid die casting. And as well, you have also some opportunities to develop new tooling concepts. This slide also adds this was John Weiler already mentioned. But John, one comment to you, I think Ford is as well on the way on the big castings. But we have the three areas. The European ones are still believe on 4,400. We have some of mass production. They don't decide where I have to go with big or not too big machines. And as well, you see we have the first mover. We have Tesla, we have Ford, we have Volvo, and we have for sure the Chinese newcomers. Artificial intelligence. This is the third one I will show. And why do companies have to deal with AI? It's offered by IT department as a new service, or as modern, or as cool. It will probably be important in the future. It is maybe the best way to have a process optimization. But often your data were collected in the foundries as manufacturing data, performance data, sales data, contract data, but it shouldn't be in the right form. After that, you have to do that with data analytics, and you have some software for that. And after that, you take the key AI and make a prediction model. But using an example of a die casting component, it quickly becomes clear what variety of data must be foreseen. Special attention should be paid to the appropriate assignment of the data, whether this data makes sense in the evaluation of the individual events. If the data forensics is not performed correctly, a wrong learning curve can be generated very quickly, and thus leads to a wrong prediction. In the experiment carried out here, the startup curve of a product or its startup scrap was examined, and after various iterations, this leads to a massive reduction in the ramp-up phase for scrap, as you can see here. The blue one is the original one, the red one is supported by AI, and you see that it's very, very fast, and we have less scrap. If you want to have a closer look to this topic, I recommend to have a look on the open source in the World Wide Web. It is amazing which a comprehensive linkage of this data is freely accessible. We at GF Casting Solution will also have a further deep dive with AI in the product development. For sure, we will still work on operation side, and we will also start to have some material development, or we try to. So, as you have seen, you always have a lot of possibilities, but you have still no product or no idea, and therefore you have to read it carefully. Innovation, that is what you needed, is a multi-step process by which companies transform ideas into new improved products, services, or processes in order to successfully compete and differentiate in their marketplace. Recognizing a development cycle as one of the important tasks in our industry, because if you miss it, you won't be able to get the product for about approximately 7 years. And therefore, this S-curve is very important to be an early adopter. Using current battery technology, as also already mentioned, as an example, I would like to show that it is a chance from lithium-ion technology to solid-state technology. The battery cases will not have to look anything like they do today. And one of the manufacturers that has already made this public is NIO. They will go for solid state. This task now is to develop the needs of tomorrow in terms of requirements, component size, functions, and charging technology as sustainability as possible, perhaps even with the existing equipment. This technology could again be one of the game changers between built battery systems and cast battery systems. This slide rapidly makes clear what the described factors of the future will be. Digitization. Is it advancing very fast, and what impact will this have on components? All these functions require visualization, and this requires electricity. Or better ask, what opportunities does it offer to integrate functions? Therefore, you have to do a so-called technology scouting. And below it is plotted the time on the bottom line in which it could be implemented. At the outer radius, the technology fields are plotted as an example. The numbers in the bubbles are simply a list of ideas, sources, and do not represent a ranking. the size is the the bubble size is a possible maturity level. And with this tech radar, you can identify technologies, benchmarking, IP rights, external best practice, all the market trends, customer insights, and a lot more. And from that, you can have some clearer points where you have to go. From this tech radar and the concept proposals on the market, the task now is find the right product. A possibility could be driver experience, which will change in the future, and that directly changes the casting products behind. Transfer of functions to the component service or the other functions in the center console never look like it looked today. For example, e-bikes, where the function move into the components, or public transport, which in the future will also take over functions in the seat structure, and the structure is also a casted structure, and find their way into the window frame. And the window frame is also casted. So a lot of opportunities. How can look these ideas? You can see two examples for the battery housing. The batteries, they have as we know, there are a multitude of requirements that today's batteries have to fulfill. And the focus is certainly on the modularity of batteries to serve a variety of platforms. The crash safety, and due to the different concepts, which also challenge the joining process. Magnesium could make a significant contribution to lightweight construction. In the upper right, here, you can see a concept that already casted that focuses on sustainability production and the easy scalability. And the boundary condition for this concept was to produce on the existing 4400 a precasted cooling structure, a cast-in crash profile, and an innovative joining easy click connection, which ensures tightness, crash transition of the profiles, and as well the stiffness. Below right, you can see a concept in which the combination of a cast magnesium frame, substitution of the aluminum frame, with magnesium, it would be also possible in the future to extend the whole with magnesium sheet in the bottom, maybe. Or infrastructure charging stations. A new field of activity for the die casting could be to combine the functions of the support structure. Maybe you do that by bionic design. And the liquid cooling. This special feature is to develop heat sinks which function maintenance-free and highly efficiently, so that the classic liquid cooling is no longer necessary. The next chance is, using the light bulb as an example, I would like to illustrate how standard consumer products can quickly and easily become so-called smart products. The function of the energy-saving bulb was expanded with individual color design, and that's it. Result, 10 times higher value. The task now is to copy this example for die casting components and to adopt extended functions and following the way of shown slides, deriving the trends, using the tech radar, develop your product strategy, and then create your idea. What this might look like, which is shown in the following slides. And the basic structure are well known today, and the digitalization is advancing steadily. So why don't we simply adopt the screen frames, ventilation systems, in the crosscar beam, or the lightning of the door control elements? Even the center console can directly take over the cooling unit, the induction coil, or the control element holder. Even the seat frame can take over the ventilation supply centrally and also the brackets of the electric motors if we have a good product idea that also supports the lightweight construction. So we're already there and we can start. And now, if you have now the chance to produce visible parts in the vehicle interior, as shown here, it is obvious to integrate the so-called ambient lighting into the components. It is also easy to integrate screen frame for displays. Furthermore, it's only a question of time when such visible components are combined with the underlying cross-car beam, for instance. The new components do not necessarily have to follow the old component design rules, but can, of course, also take into other forms. Developments. For those who don't know GF casting solutions, here are some examples of our products. One of the requirements is to manufacture products on existing equipment with no or minimal machining. The center console on the right-hand side, for example, are only equipped with cable edge protection and delivered to the customer ready for assembly without any machining. Especially with large components, the dimensional tolerance is a special requirement, and therefore you can also ask for magnesium, which has quite some advantages compared to aluminum. Here, the development of a spring tower. The development approach, why should a spring tower look like it looks like today? And why should it be made from aluminum? Current status was, or is a market analysis is done, basic investigation, comparison, aluminum structures versus magnesium structures, and initial dynamic testing, aluminum versus magnesium. And as you can see here, we have done a lot of market research, and they look all different. Then we have done a development with changing the material, including the bionic design. And we have also some quite good results. We are lighter, and the load cases we also fulfill with magnesium. Of course, we have to adapt the surface of the product, but it's not a rocket science thing. Max seats and components. In order to achieve further lightweight potential, it is interesting to consider magnesium seat structures in both the aviation and the automotive industry. Today's steel seat structures are already very well implemented by means of excellent lightweight construction, especially in the aeronautics. Therefore, the current lightweight construction must be countered with an intelligent design, and the high crash requirement in the critical areas must be met by a combination with other materials by means of composite casting, and that is possible with magnesium. The known requirement regarding contact corrosion can be well prevented with a suitable pre-treatment of the inserts. And how we do that, for instance, here an example on the cross car beams, who is in the last years this famous part we developed. In the first, on this basis or this slide, I would like to show that is in general, and as far as a customer provides the installation space, the complete development can be carried out by us. This is usually done by the topology optimization, linear finite element analysis, and NVH simulation, a special interaction of the design space with the requirements of the different disciplines, and of course the cast component design. Here you can really imagine how difficult it is. In addition to stiffness, in recent years, the product are also taking on more and more crash requirements. And that, of course, is a driving force, lightweight construction. The example shows impressively on the basis of a premium vehicle, that existing lightweight construction can be improved even further through the use of magnesium. In the case of megacasting, you also have to ask yourself, why aluminum? The existing aluminum casting concept required in-gate cross-sections, for instance, wall thicknesses necessary for casting, which therefore cannot fully exploit the lightweight potential of aluminum. With a suitable design, magnesium can bring its full lightweight potential to the megacasting by its better flow behavior. And of course, a suitable coating concept must also be used here, and composite casting may also have to be considered in this case. And that is what it can look like. We have done a simulation with the magnesium material to see what we can fulfill with which machine size and so on, but it's still under development. Now the short look to the sustainability. That is important in the last upcoming months. As is known, the best way of recycling is to have no recycling. The recycling path of today's magnesium products seldom comes back to the foundry, even not sorted by alloy, but rather often migration to other industries is seen. In the future, it will be necessary to close the loop more and more, which will make recycling much more energy efficient compared to the primary route. Furthermore, in the future, a reuse of the product should be considered, for example, in another industry, like the battery cases from vehicles into storage batteries for the households, or possibly with a slight adaptation in a new vehicle. And for sure, we have to exclude the lifetime stressed components. They don't want to have a reuse or a second use in the same geometry. We are already making constant efforts to reduce our energy turnover. Based on 2019, our energy turnover consists of 6% for gas, 16% for electricity, which already comes from solar and hydroelectric plants as far as possible, and 78% which comes from the material supply. But the 78% is the average, including aluminum. It is therefore quite clear that in the future, we will increasingly focus on our interest to material production from sustainability generated material sources. An overview of the future sources generated with sustainability green electricity is available from the IMA. And because the sustainability is at the heart of our strategy, we already deal with the recycling cast alloys, but we have to improve the CO2 values, as shown here on the left-hand side. Oh, sorry. And the future values will be reachable with new magnesium raw production sites, because all of them are planned with renewable energy and improved routes. These new raw magnesium production projects are being planned or implemented in Europe, the USA, and of course in China. And all these projects take into account to the reduction of CO2 values. However, it is also particularly important that Europe resolutely resettles the production of magnesium. It is not only the lower CO2 values during production and the independence that are important, but also the short delivery routes that will improve market acceptance. One of the really important points. Of course, this will not be tomorrow, and by the time the mentioned projects start their production, it will be certainly start at 2025. They reach by 2030 a market share in Europe between 15 to 30%. It's still the opinion right now, and that will give confidence to the OEMs and the market acceptance, and the confidence to the OEMs. That is what we need. and then I'm done. So hopefully I have inspired you, and I'm open for questions.
Thank you, Michael. Also, thank you for stressing the sustainability topic and the process for showing the OEMs and our customers that we are willing to provide a sustainable, more sustainable product in the future. Also from the primary route, but also from the recycling route that the magnesium takes part together with all the other materials in a greener future. I also realized that I made a mistake in my introduction to Michael. I used his currently topics on material simulation using artificial intelligence. So I said aluminium. So I apologize for that. So artificial intelligence is not yet on my desk. So sorry for this. We have some questions. I think they're already answered in the chat. So I will go over through the last presentation of today to the company 595 Solutions, who is the youngest member of the IMA in the trio today presenting. And I would like to give some credit to Achim Sach, the managing director of 595 Solutions, but the presentation will be given by two colleagues, and one is Mr. Arne Amann. Mr. Arne Amann has a degree in social economics from Surrey and Magdeburg, and he has worked the last 15 years in different management positions in companies which were steered or owned by private equity funds. And since January 2021, he is the CFO and shareholder of the company 595 Solutions. And his colleague who will do the second part of the presentation is Mr. Christian Platzer. Christian has a degree in technical physics, and he has founded and managing a company called Dynamic Metal Systems R&D, and the company is dealing solely with Thixo-moulding. And no wonder that they work together on a project of battery housings and flame retardant alloys with 595. And the topic of the presentation will be hybrid magnesium aluminum castings and process development in the magnesium Thixo-moulding process. So over to you.
Thank you very much, Martin, for the introduction. I will very quickly introduce 595, and then Christian will take over the technical details. So 595 is a die casting company which has been around since 1948, has been taken over by us at the beginning of 2021. And since then, we have not only sort of restructured the business somewhat, but we have also started to invest heavily into magnesium Thixo-moulding, which is where we met Christian and then have developed some new product ideas, one of which we will show you today. 595 is traditionally based in Germany, headquarters still in Nuremberg, although as you can see, the production footprint is moving slowly but steadily to Romania. We now have 20,000 square meters of production site in Romania, around 10,000 in Flossenbürg in Bavaria, and a legacy machining location also in Bavaria, where we employ another 60 people roughly. Overall, there's around 550 people currently working for us. Christian, if you can switch over to the next slide, please. We are supplying mainly automotive, e-mobility and aviation customers. We try to be a one-stop shop as much as we can, from the development, obviously, casting, machining, finishing. We have a coating line in Romania as well, and we assemble wherever it is required and desired by the customer. As I said, magnesium is something which is fairly new to us. We have won sort of the first couple of orders last year. That we will be running 850-ton machines for this year, next year, before we move into something a bit larger. The development idea, which we would like to discuss today, is a hybrid production process, which Christian will now be happy to talk you through. Christian.
Okay, thank you. Also for the introduction. As Arne said, we are mutually working on a new concept to produce battery housings. And the problem that we are trying to solve is that, from our point of view, current battery housings are still too heavy. They are still too expensive. And usually they cannot use magnesium, or at least the tier ones do not yet use magnesium in battery housings. And as we are focusing on Thixo-moulding, we have no other option than to use magnesium alloys, and that's why we try to figure out a way in how we can also apply it to battery housings. And because Michael just has said that sometimes this IMA webinars can inspire ideas. It's funny because actually this idea was somehow inspired by one of the presentations of last year, which was introducing the possibility of joining aluminum with magnesium. But back in that time, there was not, no one could answer the question what would be the application for it. And I'm quite confident that we found one application for it. So let's go into more detail. Today we already learned a lot about battery housings. Maybe I can add something to it that we learned during our investigation of that topic. As I said, currently mainly aluminum is used to produce battery housings, and they tend to get bigger and bigger. Maybe in future they can get a little bit smaller if the chemistry behind it can be somehow changed or improved. But currently they're getting bigger and bigger. And the first thing that was used to produce those battery housings have been aluminum extrusions or aluminum profiles that got assembled. And the advantages of those aluminum profiles are that they have a very good flatness, which is important because we need to control the temperature of the battery cells in the housing. And this is usually being done by controlling the housing bottom temperature. And the bottom is via heat transmission, influencing the temperature of the battery cells. And to assure a good heat transmission between the housing, which is the heat exchanger, for the battery cells, you need to have a very good contact surface, and you need to have a good contact. And therefore you need a good flatness. And this is something that extrusion profiles can provide you right away. And extrusion profiles are quite cost advantages for big surfaces. And they have the advantage that they already can provide you with the needing cooling channels that are being used to control the temperature of the housing. You need to pump through some coolant, and with the profile, you have those channels right away from the production. And they like to use aluminum profiles because they fear corrosion, of course, from the housing with the coolant. And this is one of the main reasons why they don't want to use magnesium in battery housings. But there are also disadvantages in using those profiles. They assemble them from many, many different parts. Like we heard in the first presentation, that this is basically the idea why you want to change to big castings, because you want to prevent disassembly lines. And because they in total add up to quite high costs for the battery housings. So what we are seeing at our customers is that they somehow go away from these extrusion profiles and try to go into big castings, but aluminum castings. The advantage is that you only need a few parts. One part is not possible because we need to somehow create those cooling channels for the coolant, and they cannot be casted. But by having this single big shot, you can save lots of costs. But even in this evolution step, you have some still remaining drawbacks that we will also investigate in the next slide a little bit closer. You still have a high investment in very big machinery. We have dropage from the casting that we somehow need to deal with, and to close the cooling channels, we need a welding process. So this is an example for a rather small battery housing with a dimension of 700 millimeters to 1 meter. And the requirements that we need to meet is, for example, flatness of plus minus 0.6 millimeters in the contact surface to the battery cells. And to achieve this flatness, usually the aluminum die casters have to mill the complete inner surface of the housing, and also the backside, because the backside, number 4, is being covered by an aluminum sheet that you need to weld on the bottom. And before you can weld it, you also need to machine that surface. At least this is what we hear talking to many companies that are doing this. And by considering this rather small dimension of a battery system, you already need a 5,500 ton machine in aluminum die casting to be able to cast it. And although there is this hype of die casting machines getting bigger and bigger, we somehow learned that there's not so many on the market, and it's very hard to invest for the foundries into those die casting machines, because the volume of the number of the needed battery housings, for example, is not so big. So usually you cannot fill your die casting machine with only one contract. So it's hard for the tier ones to find enough suppliers. And now I would like to come to the thing that we are doing or trying to do. We are trying to combine the best things that we can get from aluminum and from the extrusion process with the advantage from magnesium and casting. We are using the aluminum profile for the basis of the housing because it provides us with good flatness at low cost, even in big dimension. We already have the cooling channels inside, and they are ready to be flown through with the coolant. And the disadvantage of the profile is that you cannot bring functionality and complexity into the geometry, but this we can do with the casting process. And because the frame of the housing is not in contact with the coolant, usually when the battery system is on the bottom of the car. Also, only the bottom of the battery housing is in danger of being of getting in contact with the surrounded air. So we can apply magnesium in the battery housing in this surrounding structure that can give us a big advantage in the total weight, because the total weight of the battery currently can only be influenced by the weight of the housing. You cannot take weight out of the battery cells, because this would be a drawback in the capacity, of course. So we can only save weight in the housing, and magnesium is a very good way. Only because of the lower density, we can save lots of total weight, and we only apply it in the areas of the housing where we do not have to deal with the drawbacks of the magnesium, like corrosion. And this rather small battery pack. In die casting, if you want to make it in one cast shot, you would need a 5,500 tons machine. And with our strategy of over molding the aluminum profile, we can do it with a 1,600 ton Thixo-moulding machine. And the reason for that is that we do not need to clamp the area of the aluminum profile. We only need the clamping force of the machine to clamp the projected area of the casted material. And the casted material has a very small projected area. Or the area in between where we are placing the battery cells do not contribute to this projected area, and therefore the machine can be much, much smaller. And the size of smaller machines are much more available on the market than the big tonnage machines. And in this case study, we have been able to reduce the weight of the battery housing from 16 kilogram to 12.7 kilogram, providing the same geometry, more or less. And the technology we use for bonding the magnesium onto the aluminum is the over-molding of the aluminum profile with semi-solid magnesium. And we are doing this into laser structures. So there's a preparation process where we need to structure the surface of the aluminum profile in those regions where we want to overmold the magnesium. So basically the area you need to prepare with the laser is the same like the projected area of the magnesium. And we have already tried different laser structures, and this is also something we are continuing. There's many different institutes and companies that are focusing all the research on the perfect parameters for lasers. And we learned a lot in the last months of what's working good and what not so good. But we have been able to produce smaller prototypes with this concept. The box you see here has a edge length of 150 millimeters. We have done a very simple prototype just to prove the basic functionality of the idea and check out how good is the bonding and can it be tight. So we purchased a very simple aluminum profile, a standard alloy, and put the laser structure onto the needed areas, and then overmolded it with the Thixo-moulding process. And even though this is a very, very small prototype, we already have been able to show the basic idea of saving money in needing only ton machine in cold chamber die casting or any casting machine or cold chamber die casting because of the pressure, you would have needed a 400-ton machine at least. And by using the aluminum insert to take over most of the projected area, we've been able to do this on a 280 tons machine. And the result after some trials has been already quite satisfying. We have been able to provide a bonding that was media tight and also showed quite good peel adhesion, because it's not so easy to classify the bonding actually, because the bonding that we are creating with this is not it's not, the magnesium is not melting the aluminum when it's over molding the aluminum. It's just flowing into the lasered structures, and those lasered structures are showing back cuts. To give you a better understanding, the left one that you see here is the aluminum profile, and the right one is the Thixo-molded magnesium. You can see also the solid particles that you will always see in a Thixo-molded product, because we are not melting up the magnesium completely. We are working in the semi-solid region of the alloy, and the advantage of the Thixo-moulding is also contributing to this bonding technology, because the shrinkage of the magnesium alloy is much lower than in die casting when you are overmolding with overheated magnesium. So it's easier for the magnesium to stay in those laser structures without getting pulled out during the cooling to room temperature. The laser treatment that was so far most successful had a speed of 3 to 5 seconds per square centimeter. This is quite slow if you want to make big battery housings, but technically it's possible to also use multiple lasers to increase the cycle time. The lasers that are being used to do this are conventional lasers that can be bought on the market. Usually the IPR for the laser structures is the parameters that you use to create the grooves and then the microscopic structures of this interface. Here's some nice pictures of the prototypes that we have casted in Germany. We are quite satisfied, but we are not yet there. There is no big prototype yet. So for the next things we are going to do, we are still testing further laser structures with different geometries. We are already working on solutions for the automation of this process, because we also found out that the laser structure needs to be quite fresh before overmolding. So there needs to be a just-in-time lasering next to the die casting machine. And we have already started to develop a larger scale prototype similar to the size that you saw at the beginning of the presentation. So thank you for your attention. I hope it was interesting for you.
Thank you, Christian. Thank you, Arne, for the very interesting presentation and the way to go with a new process. I suggest that we switch into the mode where we can only see the panel. So I think, Christian, if you stop sharing, yeah, okay, good. Yeah, with this, I would like to open the Q&A. So we have about 10 minutes according to our schedule. I see no questions in the chat yet. And let me start with Michael. Michael, you presented on the side a very interesting, and I know it's not very public yet, on the NEO solid state battery housing. So can you share some more details, because I think that's a very interesting part, especially from the magnesium housing, but also of course from the solid state battery, because at the moment we see lithium in several variations being the future, and solid state is always like 10-15 years ahead. Can you share more about that?
But what you can see in the presentation handout, you will see what is their statement at the time. I have no insights, no further insights. I hope we get them, maybe through a colleague, but they will build up a production for solid state batteries. And also the time frame is not 10 to 15 years. This is more in 2 to 5 years.
Okay, that's good to hear, and that's happening in China. Is there any, I mean, you know, any insights if solid state is more advanced there for the next generation?
No.
Okay,
not at the moment. I heard some things about solid state from Daimler, but no clear facts, and so there we have to wait.
yeah, because solid state is always like in the magnesium corner as well. You know, that's also it's both interest, both the housing, but also the chemistry. You know, please roll in your questions if you have any. As good moderator, I have of course another question prepared for you, Christian, and you, Arne. I mean, you're obviously going for this overmolding. For that's, at least to my knowledge, a new way of integrating two materials like aluminium and magnesium. So your battery housing is the first example. Can you share any other examples or thoughts what you are going to develop or are developing on other?
Well, there is a company in Germany that has a quite similar process where they combine metal and plastics with something which is, I would say, a similar principle than the overcasting. The company is called Hydroin. They're based in Dresden. And we've known them for many years. And this laser structuring that we have applied to our prototype was done by them. But they are not casting, they're not a casting company. They're building special machines for cleaning, and now they have ventured into this joining technology. But as far as we know, this is the only other example where such a process is being used, although this lasering is something that is being looked at by various institutes. But from my understanding, they are always trying to combine sort of equal materials. They are not looking to combine one metal with the other, or one metal with plastic and what have you. So yeah, there you are. I'm not sure, Christian, whether you...
As we remember in our industry, we had the magnesium aluminium engine block from BMW some years ago. So there were an example of combining it in the casting process already. Is John here, or has he left already? I think he left already. Yeah. Okay. So from the colleague panelists, do you have any questions or statements to each other, or some other additions to the webinar, as I see no questions rolling in?
I would have a question to Michael. I think you can answer. The giga castings for magnesium, how much, what is the biggest shot weight that has been casted in magnesium so far? Because I heard from the giga castings for Tesla, they have a shot weight of 230 kilograms. So it would be interesting to hear what is the maximum that has been done in magnesium.
I don't know. I never heard that they casted 200 and above kilograms, and that magnesium, I don't know. I have no experience. I know what we have casted on 3,500 and 4,400, but never never in this range 100 kilogram above. I know that they in the former times they casted whole frames in France and in Germany, but they never gone in serious production, and they casted it in gravity casting, mega castings, so like the complete underbody. But yeah, I have no.
I see some questions coming in. James here is asking about at a discussion about the average kilogram of magnesium in a car. So this is I think always a very interesting question, because it can be misleading, because you have cars or with kind of for us, you know, we view a lot of magnesium, which is in the range of let's say above 20 kilograms per vehicle. The average, what we normally state, is between 3.5 to 5 kilos, so depending on which consultant you are listening. Normally in North America, the average kilograms is a little bit higher. So that's normally the range. We don't see at the moment a significant increase in electrified vehicles. So we see that the classical magnesium parts in higher value cars, in a way like an instrument panel, which was shown today, or an front end. However, the front end is a little bit different because of no cooling necessary. So this is a crossover part, we could call it, into the next generation of vehicles. Plus there are new parts, like there is more infotainment and information systems in electrical vehicles normally. So this is like these curved screens. What you see is most probably a magnesium housing. So it is an electrified vehicles enables us to for new application, but we don't see a big change yet. A battery housing, I think would be a great chance when some like magnesium or any kind of combinations could be like a reference product for electric vehicles as a certain range or class in the future. There is another question about the mega casting and the risks. I think that's why I would like to ask John here. But Michael, can you elaborate on that? Because we heard about this, and there's a lot of investment into such big machines. You need them filled. Also if the castings are not as you know, the waste is significant higher than with smaller machines. So is there any?
That's the huge figure, and it's difficult to answer. Therefore, I addressed it in my presentation. We have to make clear that somebody has a strategy, and the OEMs, they change often their strategy, and therefore they want to have it or they don't want to have it. Therefore we need a market acceptance, and therefore we need sourcing or good sourcing opportunities, and then you can overtake these challenges to get magnesium in the car. If it is more dangerous, I don't believe so. I think with magnesium, and Christian and John has shown it as well, you have opportunities to fill better a big casting with existing equipment. and all the other things, if I understood it correctly, danger, the material is not more danger than aluminum. You have to be careful and you have to do some preventing things, but yeah, it is.
Yeah, I think that the question was not more about the magnesium as a material. It's more or less at the risk of the casting process, you know, into investment and so on. But I think it's clear that it bears a risk, and that we in the magnesium industry have already invested into big machines.
Yeah,
for us, big machines, and we can do bigger parts than aluminium in similar clamp forces. So that's clearly an advantage.
Yeah, but if you compare, if you compare that what Christian said, and as I mentioned as well, you do that magnesium with compound casting, and you don't need such a big machine. That's clear.
So we have to call our castings giga castings as well. So to be on a trend. There's another question from William about the energy usage. I think it's a typical, precise question for you, Christian, to compare energy usage of Thixo-moulding to cold chamber high pressure die casting.
I don't have the figures to compare it with high pressure die casting, because to my knowledge they are using also gas as energy source.
Maybe I take that. So I think the difference between high pressure die casting and magnesium Thixo-moulding is that the die casting also requires the melting of the aluminum, which is a separate production step, and which is done either with gas or with oil. I couldn't tell you exactly what sort of the difference in energy consumption is between the two processes, because obviously it depends on the size of the machinery that you compare against. But I would suspect that in terms of sort of energy density, the aluminum die casting requires more energy than the equivalent magnesium Thixo-moulding process. Although I couldn't tell you a number. You would have to look at it sort of with a comparable part on a comparable machine, and then really sort of do the one-to-one comparison.
Thank you. I think those data are available from the machinery producers.
Maybe I can add something to that question. I think the question was more compare magnesium Thixo-moulding and magnesium die casting. And I saw a presentation from a German Thixo-moulder who also has hot chamber die casting. And compared to the hot chamber process, it's 20% less electric power consumption and no gas, and they need additional gas, but I don't have the numbers for cold chamber die casting versus Thixo-moulding. But I'm quite sure Thixo-moulding uses less, just because we use lower melt temperatures. So yeah.
Okay, thank you. I think because of the time, we end this webinar. I think it was very interesting. I hope for you as panelists. Thank you very much, and also for the participants. If you have any questions, you can email the presenters themselves, so you can email us, and we will forward it or try to answer it ourselves. If you have not done so, visit the IMA website, look out for our next events and our news. We are constantly trying to provide our members and the industry with news and interesting facts about the magnesium industry. So in about a few days, I think the recording will be available on the IMA website and on the IMA YouTube channel. And I hope you had some good takeaways from it, and I wish you a nice remaining day. Thank you very much. Bye-bye.
Bye-bye.